So hi everyone. Today we are pleased to have Ann Collins joining us in person. Ann is an assistant professor in the Department of Psychology at University of California, Berkeley. She and her lab studies human learning, decision-making, and executive functions using computational modeling, behavioral, EEG, drug, and gene studies in healthy or patient populations. Her fun fact is that she once sang as soprano soloist in Mozart's Requiem on an aircraft carrier. So please join me in welcoming Ann.
Thank you for the invitation. It's lovely. I think this is my first in-person invited talk since the pandemic. I've given a talk at in person at Berkeley before, but it's really nice to see other people in person finally. And I realized, I won't be able to see you smiling or frowning when I, say things. But hopefully, you guys interrupt or use verbal cues to help me along. And I'm very happy to make this as interactive as needed. So feel free to ask questions as they come up. I reserve the right to run them to the end if it makes more sense. But yeah. Okay, so thanks again for the invitation. And today I'd like to tell you a little bit about two projects we've done in the lab that show that reinforcement learning is not a process that occurs in isolation in the brain, but rather that it really depends on other processes, in particular executive function. So something I'm really interested in is how humans are able to learn so flexibly and efficiently, and especially compared to other non-human species. And I think a lot of that depends on actually really all circuits that support reinforcement learning, but that gets really repurposed through interesting inputs from other, maybe more advanced circuits like executive function networks. Okay, so we've had to do, to become super flexible. We've had very good examples of like how quickly the world changed and how quickly we can adapt to it lately. So, we do all kind of things where we adapt quickly, like getting a new device or a new laptop, or, learning how to handle a squirming baby, but also learning how to handle Zoom each time it changes again, or how to verify if it's not Berkeley, or, how to handle an online conference, right? We've had very good examples lately of, having to change our routines and behavior. And we're pretty good at it, right? I mean, who would have thought that we would all be in a room wearing masks, 2 years ago, right? So I try to understand how we do that. And I work from a framework of reinforcement learning. So reinforcement learning is a very broad class of many things, actually, but in particular, algorithms that broadly assume that there's some kind of state that an agent is in. That this agent has access to some choices, and those choices lead to next states and also to something that can be interpreted as a reward. And this reward has an impact on the algorithm itself that can learn and update how we make choices. Okay, and I mostly focus on one of the simplest algorithms, but this is not obviously exclusive. The simplest algorithm is to say we're doing something like error-based learning, which is saying that we estimate the value of something, this Q here, and we update this value in proportion to an error term that is this reward prediction error here. So the difference between the reward you got and what you were expecting. Now people on Zoom see if I point this way or?
Yeah.
Yes.
Okay, great. Good, thank you. So this is a functional algorithmic level that, Mars algorithm kind of level. But it's been super successful in part because it has something of a counterpart as a mechanistic level kind of model. So there is a network in the brain that is super approximated here, but essentially cortical basal ganglia loops with dopaminergic input that seems to approximate something like this algorithm. And because this algorithm also approximates some aspects of behavior really well and some aspects of the brain really well, it's been kind of a success story of how all this goes together. To a point that NIH sometimes tells you that don't do reinforcement learning anymore, it's old. I would say fully disagree with. Okay, so this is what I start from. But what I would like to emphasize today is how much is unknown in here. In particular, things like what the state, the choice, and the reward are. Okay. And what I'll try to convince you of is that other processes in the brain, particular executive functions, broadly construed as a very vague word, I acknowledge, contribute really importantly to setting what the states and choices and rewards are, and enable us to use this very simple algorithm to learn much more interesting stuff. Okay, and one way in which executive function contributes is by actually bypassing this algorithm through working memory. I've done a lot of work on this, but I'm not going to talk about it today. But the other way is in defining states, for example, relevant states for learning, for attention, inference, creating latent states, etc. This is also something I won't talk about today, but the idea here is that, you know, if you take this as an input, which a robot might get, you know, that's super highly dimensional, and a ton of it might or might not be relevant. And so you need some kind of attentional or filtering process to make the state much more interpretable, and so something you can learn. Okay, so there's been plenty of people who've done research on this. I won't talk about this today. What I would like to talk about today is the importance of executive function in defining what the relevant choices are over which we're learning, and what the reward function is that we're learning. Okay, and so in the first part of my talk, I'll talk about what a choice is when you're considering reinforcement learning. And in the second part, I'll talk about what a reinforcer is when we talk about reinforcement learning. Okay, so what is the choice? Well, you can think of choices that you make at many different levels. So the simplest choice you might think about is a motor movement. That's the thing that you might think your brain is controlling, just, you know, like sending motor commands to your muscles. And then you might think that this motor movement is, for example, in the service of a key press, which in this case might be part of a key combination. That might be Control C, for example, for copying, which might be like a slightly more abstract choice to duplicate this blue box for this presentation, which might be part of this goal of making a figure, which might be part of this goal of making a presentation, etc. Okay, all of this you can call choices, right? And there's a very clear hierarchy of abstraction in those choices, but you could decide to model choices at any of those levels. Okay, and it's not going to be trivial what the impact of the choice of as a modeler or as an agent of selecting any level is going to. Okay, this is just to establish that this is not a trivial question. Okay, so how do we define what the relevant choice is? So we, you know, this is a big question, and I'm going to simplify it a lot for an experiment here. We're going to just consider two levels, one of just motor actions, for example, pressing on the brake to stop, or slightly more abstract choice of choosing an item, which might require different motor commands to do so. For example, you might decide to select the burger or the corn dog, and you might do that either by speaking to the vendor at the restaurant, or you might do that by you know, clicking on an item on the menu or something like that. Okay, so we wanted to try to understand how this type of different choices impacts how people learn reinforcement. So we developed a very simple task where participants could do both types of learn from either types of choices, and we just tried to understand how that impacted their learning. Yeah, so we had a simple instrumental learning task for participants. So stimulus on the screen, here the star, for example, made one of three choices, in this case, left, middle, or right, with corresponding finger presses. And then got binary, deterministic, truthful feedback, and unchanging, telling them what was correct. Okay, so here the middle key was correct for the star, and the other two keys were incorrect. This is the position condition in which really what matters is which key press, so which finger you press. Oh, and this is so one condition. And here I'm showing you just a single stimulus, but participants learned about 6 different stimulus action associations, randomly interleaved. So this is not realistic to find with this 3 in a row happening. Okay, then we had another position condition in which participants essentially had to do the exact same thing, but there were the boxes in which they on which they pressed had colored labels on them, blue, red, or green. And in this type of blocks, participants were told to just ignore the color. So they just had to press to do the same thing as here, plus ignore the color. Okay, so still low-level motor choice. In the third condition, participants had screens that looked exactly the same as in this condition, but instead they were told that this time what mattered was the color of the box rather than the position of the box. Okay, so what they need to learn here is to choose blue for the hexagon rather than choosing left, middle, or right. Does that make sense? Okay, so this is a more abstract type of choice because once you've selected blue, you still need to make a motor action based on the fact that the position of the box is randomized. Yeah.
Are they responding with 3 buttons laid out like that?
Yes.
Right. So it's easier that way, but there's some potential SR compatibility issues there, right?
Yeah. So we didn't confound the position versus motor aspect of the experiment. You're completely right. Any other questions? Okay, so we had those 3 conditions. There were 3 blocks, label blocks, 3 position blocks, and 2 position control blocks. So we first ask, okay, so how does learning impact this? And the first thing to think is that as far as you go in the reinforcement learning literature, it shouldn't matter. You know, if you're a modeler, you're going to treat those types of choices exactly the same way. You're just, you know, especially given that participants are instructed, you know, what the choices are that they're making. You would just model, you know, this has 3 choices, blue, red, or green, and this has 3 choices, left, middle, or right. You know, if you code that in your computer, it's going to be exactly the same. Okay, but intuitively, as psychologists, we think, you know, that might actually be not right. Okay, so this is what it looks like. This is a learning curve, proportion of correct choices as a function of the number of times that a participant has encountered a given stimulus. And so you see that participants learn in all conditions. They learn equally well in the position and in the control position condition. And they learn much slower in the label condition. Okay, so the type of choice you're making matters. Impacts how you're learning. So that's the first thing we wanted to establish. The second thing we wanted to establish is how specifically matters. Why do you learn slower in this label condition compared to the position condition? So remember, the label condition is a condition in which you are making a slightly more abstract choice that requires you to make a downstream motor action. Okay. There is also, you know, a potential concern for difficulty in the sense that because the colors change, whereas the positions don't change, you have to search for the, you know, where the blue box is. But to try to alleviate this concern, one thing we did was to show the boxes first for 1 second before we showed the stimulus, so that the participants had the time to encode this prior to that. Yes.
I think I might not be getting something. I'm kind of wondering why they don't get to 100% accuracy. The task is pretty simple to me.
Yeah, so it would be very simple if you're learning 2 stimulus action associations. They're learning 6 stimulus action associations in each block. So I'm just showing 1 each time, but there are actually 6 randomly interleaved. That's beyond what you can do with just memory, short-term memory, and so it does tap into error, and we'll get to that a little bit later, which is why they don't, if they had perfect memory, they should really be at asymptote by iteration 3, right? Which they would be if there were just 2 associations. Yeah.
How much of the setup is sort of given away to participants? So do they know
Yeah.
that it's deterministic and unchanging?
Yeah.
They just need to
It's
learn
all
that
given
kind of
away.
thing?
It's all given away. Yeah. They know that the rules don't change. They know that they can trust the feedback. They experience it too in practice, and they know which condition they're in very explicitly. Yeah. So there's no inference or,
And
tricks.
then in terms of how it's presented, it's in some kind of blocked design.
Yeah.
We go through the different
Yeah.
stages.
Yeah. So there's 8 blocks randomly interleaved for the different conditions. Yeah. Other questions? Okay, so we wanted to make sure it wasn't just difficult to confound, and we think it's not partly because we limited this risk by showing the boxes ahead of them. But one thing we did was look at what kind of errors participants made in particular. So one thing you can think about is that if you're in this position condition, right? So where you're supposed to press left for the hexagon, for example, if you make an error, you could pick the red one, the middle one, or the right one, right? But the right one is going to be an interesting type of error, right? Because blue, you picked left before and blue was rewarded, right? And so if you're picking, if you tend to make an error where you pick blue more than red, that might indicate, that there's some kind of credit assignment issue happening, essentially. And vice versa, in the label condition, if you're supposed to learn that blue is correct, but next time after you get rewarded for blue, you pick, the green label that happens to be on the left this time, there might be also the reverse aspect of credit assignment.
Sorry, question. Did the stimuli, so, these are the 3 stimuli you show for the hexagon. Are the stimuli different for the stimuli in the box is different for each different target stimulus?
Yes, absolutely. Sorry about that. So the boxes are always blue, red, and green, randomly interleaved, shuffled. The stimuli there's 6 different stimuli per block, and they're all different across blocks. So this is a bad example because the hexagon could never possibly be in both conditions. Yeah, I should fix this slide. Sorry about that. That's misleading. Okay, so we looked at the errors, and we looked what proportion of errors have this bias of following the other dimension of choice, essentially. And we find that in the label condition, the one where participants learn slower, there is a clear bias towards the position. The previous position, but in the position condition, there is no bias towards the label. Okay, so it seems like motor choices interfere in the label condition, whereas labels themselves don't interfere in the position condition when choosing motor actions, which seems consistent with this hierarchical representation of choice, where choosing a label then requires you to choose a motor action. And so if you're representing values at that level, so that might have an influence. Okay, so to try to capture this in reinforcement learning, we multiplex the reinforcement learning process. Instead of just learning the value of the card C, the stimulus, and the label in the label condition, or the card and the position in the position condition, we assume that there was some mixture process where you're learning 2 sets of values, but maybe prioritizing one in the good one in each block, but with some confusion from the other one at the policy level. Okay, so the policy is a mixture of those two policies with a mixture parameter that indicates how much you use the one you're supposed to be using, essentially. Okay, so when we do that, and then we can test other aspects of the model, whether, for example, you should have a learning rate dependent on the condition, or whether you should have, if you assume it's just more difficult, whether you should, participants just make noisier choices in the label condition. So long story short, I won't go through all the models, but the way you capture participants' data best is this is with this dual learning rate model here, where you assume both slower learning in the label condition and the position condition, or at least different learning, right? We don't force the learning rate to be smaller, it just ends up being smaller, but also this mixture component. So with the dual learning rate without mixture component, you can't replicate this aspect of asymmetric error distribution. The dual noise model, the one that assumes that you might just make more errors overall in the label condition compared to position condition, doesn't capture behavior as well. Okay, and so the way this model M3 here captures behavior better is by showing much smaller learning rates for the label condition compared to position condition. Okay, so the label condition is not just performing worse because it's harder or because people are making noisier choices, but because it's learning at a slower rate and also being influenced by this irrelevant choice I mentioned. Okay, so the nature of our choices impacts how we learn, and more abstract choices slow learning by being contaminated in part by less abstract choices. But we wanted to go a little bit further. Yeah, go ahead.
Just a quick question. So if you kept going, it should asymptote like to according to this model. So it should get to 1.
No,
Shouldn't?
no, because of the mixture part. So with a mixture here, you essentially will get.
Oh, I see.
You will always get a little bit of your policy that comes from something that's irrelevant. Yeah, so it won't asymptote. Okay. That said, we know that this learning is not probably due only to brain's reinforcement learning process, but also to contribution of working memory, where you just explicitly remember to press action 1 for the hexagon or something like that. Okay, so we wanted to understand whether this choice that, yeah, go ahead.
One of people actually said, so it can happen by chance, right? That in the label condition, it's aligned.
Yeah.
With what it's like. So
Yeah.
do you find according, speed up like in that position when that happens?
Yes, we do. Actually, we have slightly confusing reaction time effects. So we have a speed up one that's convergence in one of the condition, but a slowdown one that's convergence in the other condition. So in the label condition, when the position agrees with the label, meaning the position that was reinforced the last time you saw this is in the same place, we actually see slower reaction times, which made us scratch our head quite a bit. My conclusion is I don't have a conclusion. My hypothesis is that some kind of metacognitive process happening of people like being suspicious of saying like, oh wait, I want to press this because of a motor, but I know I'm supposed to label, so is this like the right reason or something like that? That's the only reason I could explain that, because it was a fairly robust effect. Sorry, I didn't show it here. Yes.
More abstract process.
Yeah.
It seems like depending on the nature of the task, the level of abstraction is supposed to be slow will vary.
Yeah.
And so I would expect then that you might have for some tasks more abstract choice spaces that actually easier to learn for the task, and that's just going to depend on how you design those. Is that fair? Or
Yeah, no, that's completely fair. Here it's everything else equated, right? So everything else equated seems like the more abstract level is slower. But certainly, if everything else was not equated, in particular the relevance or something else, that might be the case.
So for example, if you greatly expand the effector space, might expect that if you're taking decisions in an
Yeah.
abstract space,
Yeah.
and you're not searching through like the movements of your fingers, for example, you might really benefit from that sort of abstraction. But that's the case in this space.
Exactly. Okay, so we wanted to understand whether this choice process, this level of abstraction in the choice impacts all processes that contribute to learning equally, in particular working memory, reinforcement learning, or both. So we did a second experiment with the same design. We took out the control condition because it showed exactly the same thing as the control position condition. But this time we varied the number of items that participants learn about. So as to the comment earlier where it should be easy, it's true, it should really be easy if you're learning just two things. That's the set size thing. So we manipulate this number of items from 2 to 6, which we've shown in the past allows us to pull apart working memory from reinforcement learning. And then we can see how those effects change as a function of set size and put working memory into the model and see what the impact is. Okay, so here I'm going to show you the results in a slightly different format. So I'm showing you learning curves conditioned on having had one correct piece of information in the past. Okay, so it's probability of correct as a function of the number of times you've made a correct choice for this item in the past. Okay, so if you had perfect memory, you would be at 1. The perfect memory and perfect choice, you would be at 1 for all those graphs, right? Because you've seen the information. Okay. Here the full lines are the position and the dotted lines are the label condition. And you see that essentially set size 2 here, so learning 2 stimulus action association, size 3 are fairly flat, so kind of what you expect at their maximum. And then it gets more slanted as the set sizes go up. And you see that the slant starts earlier at size 3 for the label condition, and then doesn't decrease that much. Okay, so it seems like there's a clear difference here in the set size effect between the two conditions. We also looked at those interference errors that I told you about earlier. We're replicating the fact that they're present in the label condition, but not in the position condition. And they don't seem to be too set size dependent. Okay, so we show the characteristics of having both working memory and reinforcement learning in here, a label effect in all set sizes, and no effect of set size on interference. We wanted to capture that with a computational model. So we took the same computational model as before, where we have reinforcement learning operating over 2 different sets of actions, the labels or the motor actions, positions. And then we add working memory module that can also be operating on 2 sets of actions. So the working memory module works by storing information perfectly 1 trial back and then decaying information at each trial that it doesn't encounter a given stimulus. And then those 2 modules, working memory and reinforcement learning, are mixed together into a policy. So we have a 4-way mixture now, potentially, with a weight omega. And this weight captures the role of working memory. So this weight is going to be dependent on a capacity parameter, K, and the set size. And this K divided by NS is saying, like, if you have capacity 3, how many of the NS items can you actually store probabilistically? Okay, and there's this min of 1, so that you don't store more than maximum. Okay, and multiply by a maximum value. So it looks like this. If you have capacity 2, then the weight decreases with set size like this, and starting at a maximum overall involvement of working memory. If you have capacity 4, working memory is equally used for set size 2, 3, 4, and then its contribution decreases after. Okay, it's as an inverse curve. Okay, so the winning model, and then we tested whether we need all those components of the model or not to capture the data, and what's needed to be condition dependent. So that's a big family of models. Winning model is a model where the working memory weight and capacity are different for the label and position condition, but everything else error-wise and choice-wise is shared across conditions. And there is motor interference in the label condition in both the reinforcement learning and working memory module. And so when we do that, we capture behavior really well. So the full lines are participants and the dotted lines are the model. You see that the winning model is not just winning, it's doing well. And it's capturing interference errors too, although we have maybe too few trials per participants there, so it's much noisier. And the way it does this is by predicting a lower capacity for working memory in the label condition compared to the position condition. Okay, so the conclusion we draw from this is that setting the label choice space is something that impacts limited resources in executive function in such a way that those resources are less available for working memory, for just remembering activity stimulus action association, which is translated in the model into this decrease in capacity. Okay, but then this choice space is used for both working memory and reinforcement learning process for learning. Go ahead, Taylor.
It's different. It's the same model. That's two or participant behavior.
Participant level. Yeah. Yeah. Should I repeat, by the way, the questions? I don't know if people online here. Okay. Remind me if I forget. Thank you. Okay. So what I've tried to show you in this project is that executive function define relevant choices for learning in a way that really impacts what we learn about and how well we learn about it. And I just want to take a minute of this talk to convince you why this is important potentially. I know this kind of experiment is kind of a toy experiment, not super interesting in and of itself. But I think if we step back and think about choices, it becomes really interesting because choice abstraction is really essential to flexible behavior, right? So if you think about it, if you represent this choice at different levels, it's going to enable very different types of exploration or generalization. So for example, if I've learned that it's good to copy a box, and I'm representing this as Control-C, or I'm representing it as just copy, then what comes underneath becomes irrelevant, right? And it doesn't matter if I learn to copy, the right-click copy way versus the Control-C way, I still know that copying is good, right? And so it's become independent of the actual instantiation of this choice. And it's true in the opposite direction too, right? If I know how to copy by doing Control-C, copy this box by doing Control-C, I also know how to copy other things, right? And so by having this abstraction of the choice, I can, reuse it in many different situations. Okay, so I think it's really important to think of choice at the right level and how that impacts my learning. Okay, so what's true of choice is true of state. I think is also true of the reward function. I think that's much less thought about. So I'm going to tell you in the second part of this talk why I think that executive function is also crucial to thinking about rewards. And as an anecdote, actually, the inspiration for this project was started here when I interviewed here by someone telling me that reinforcement learning was totally irrelevant because no one ever gets chocolate for doing anything in real life. Which is true, right? So chocolate, chocolate is what we call a primary reinforcer. And, if you take most healthy kids and give them chocolate, or they do something and you give them chocolate, they're likely to repeat whatever gave them the chocolate, right? So it has that reinforcing property of primary reinforcers. Okay. We have a circuit in the brain that's really good at representing things that are like reward and seems to have some kind of common currency to it. So the striatum here, for example, is sensitive to primary reinforcers, but also to secondary reinforcers, which are much more abstract types of stimuli that we have learned to associate with primary reinforcers. So, this random picture here that you see here of that dude, is really, really has no intrinsic value until you've learned that you can buy candy with it, right? Okay. And we have even more abstract things where they all look the same, but you learn to convert them into value, right? So you win, you lose. This kind of, or green circle, red circle, we can very easily do this conversion to rewards. Okay, so there's different levels of abstraction here. So something I want to point out is that this is really a non-trivial property. We think of it as trivial because I think in AI, that's how you define the reward function. You define like the agent's goal is to do this, so I'm going to define the reward function as being high at the goal and low elsewhere. But try to think about how the brain does it, and take this example. We're scientists, we plot variables all the time, so you might plot A against B, and you get this graph. This is really extrinsically neutral, right? It's just, you know, dots on a figure. Now, if you have the goal to show that variable A and B are independent, you might interpret this positively, whereas you might interpret this one negatively, right? But now if your goal was to show that variable A was a good predictor of variable B, the exact same outcomes come to have completely opposite values, right? And you don't need any like 100 trials of exposure the way a monkey would, you know, to learn this value. You can just have set your goal and immediately assign this reward value. And I think it's highly non-trivial to understand how the brain does this. And my hypothesis is that the brain is very good at doing this using executive function and then leveraging it through the classic reward circuit to use this type of outcomes that are goal dependent, even though they're completely novel, to use those old circuits to learn new things. Okay, and so that's what I'm going to try to convince you about. One-shot goals are interpreted in the brain in the same way as classic reinforcers. Okay, and there's good reasons to think that might be the case, part of which is a whole literature showing that dopamine and other reward regions of the brain actually care about a lot of other information, which is not clear why it would care about it if it wasn't more influenced by external circuits like this. Okay, so you can reframe the question by taking the reinforcement learning equation and saying, well, how do we actually set this reward function, especially super flexibly and dynamically in the real world? So you don't get chocolates, but maybe you set, you know, a goal to, you know, finish your Sudoku grade or to change your font to red, and then you change your font to red, and you're like, yay, right? So that's an internal reward potentially. Okay, so the single shot sub goals reinforce our choices and recruit canonical reinforcement learning processes. And the hypothesis is that even when action outcomes are simply the realization of a single shot abstract goal, the brain's instrumental reward learning network is recruited as if it was an uninstructed reinforcement. And we also hypothesize that working memory or executive processes play a crucial role in setting this arbitrary reward function in a goal-dependent manner for reinforcement learning. Okay, so how do we test this? Yes, go ahead.
Sorry, I'm just interested in how.
Okay, I'm going to sit, sorry.
This compared to the previous study. In the previous study, it seems like working memory is a thing that you can sort of trade off against reinforcement learning. And here it seems like working memory is a key part of the way you do reinforcement learning. I don't know what. Is there a difference in the operationalizing those? What, yeah. How those fit together?
Yeah, so the question is, previously we had working memory as its own system, and now we have working memory that fits into the RL process potentially. And I think both are, I think working memory is an extremely flexible form of working memory that's meant to like do all kinds of things, and in particular, so can do both essentially, potentially. I propose that we go back to that at the end after you're convinced that I've showed that in this case, because you're allowed to not be convinced. Okay, so experiment is going to be very similar to classic probabilistic reinforcement learning task this time, with where each trial begins with showing what condition we're in. So there's a classic condition in which you can win 1 point or lose, get 0 points. So this is the beginning of a trial. So pretend you're going to be participants for a little while, okay? And then you see a pair of bandits, so two shapes, and you choose between them. So here a participant chose the triangle, and you get feedback. Okay, so in this case, you got 1 point for choosing the triangle. Next trial, you pick the triangle again because you got rewarded. You got rewarded again. Next trial, we randomly interleave other pairs of bandits. So here you choose between a square and a cross. Participant chooses the cross, gets rewarded. You go back to the triangle and the circle, you choose the triangle and you get 0 because it's probabilistic this time. Okay, so the triangle might be the better one, but with probability 90% or 75%. Okay, so participants, just try by trial and error and get rewards and integrate this reward to figure out what to pick. So far, super classic reinforcement learning stuff. Okay, randomly interleaved with all those trials is another type of trials that looks like this. So the beginning of the trial is like this. You have two fractals images with one labeled as the goal and the other one as labeled as your non-goal. Okay, so pretend you're participants, okay? Encode. Okay, so then you see a pair of shapes that you need to choose from. Here you choose the diamond, and then you get your outcome. Was that your goal? Yes, that was your goal. Okay, this is, instead of getting +1, 0 and then +1, you get goal, non-goal, and then goal. And a key aspect of this experiment is that the next trial, you'll never see those fractals again. You'll get a completely new set of fractals each time. So at every single trial, you need to re-encode. You need to on the fly encode what's your goal and what's your non-goal, and learn to pick the shape that is more likely to lead to the goal image. Okay, so this is the next trial. Pick the diamond because it lets you go last time. You get your goal again. Next trial. Pick the diamond. It lets you go twice, and this time you don't get your goal if you encoded that. It's not super easy. Does that make sense? Okay, so you never see the fractals again. Yeah. Still probabilistic. Yeah. Okay, so we have a familiar reward condition, pre-choice period, choice period between two items, and then feedback, and then a single shot goal condition in which you see two fractals. Yeah.
Are these within or between conditions? Between subjects, right?
Within.
Okay.
Within subjects, randomly interleaved. You can see that here we have 4 pairs of shapes, 2 of which will lead to goal and non-goals, and 2 of which lead to points. 2 easy pairs and 2 hard pairs, in the sense that they're all probabilistic, but more or less so. And then we actually have 2 independent runs of this, one with shapes and one with goals. Okay, experimental design makes sense. Okay, so the key point here is that because the fractals change all the time, you have no chance to practice or to develop a value for this. You have to dynamically encode this. Or of course, you could also not dynamically encode a value. You could instead do some form of planning and model building, where you could say, well, the square tends to transition me to this state that is categorized as a goal. And I'm going to actively try to pick the transition that leads me to the goal. So you could have a completely non-value based process potentially in this condition. Okay, so here's how the behavior looks like in this task. So here I'm just plotting the proportion of optimal choices, and by optimal I mean picking the item that is experimentally defined as leading to the choice more often. Okay, so we have a main effect of condition where participants learn better in the familiar compared to goal condition, and we have a main effect of difficulty that's very expected, where they learn better for the less probabilistic and more probabilistic item. Okay, those are the learning curves bend, and you see that this is at asymptote essentially. Reaction times show a main effect of difficulty, but no main effect of condition. Yes.
One question, so you took the percent optimal choice to indicate that they learned better, but maybe they learned like just as well in the other. So they've learned that it's 70%, but
Yeah.
there's a probability matching.
Yeah, so I'm going to get to that with the modeling. Yeah, yeah. So same as in the previous experiment, you know, if the performance is worse, it could be because they've learned worse, or it could be because they've learned the same but are choosing worse, right? But the probabilities are the same, right? It's 90% in both.
Yeah, that's right. It's just that the effect of hard was easy, but might be not that they
Absolutely.
took them longer to learn, but they learned it. They just probability matching the responses.
Yeah, I mean, there's a whole, maybe we can go into that at the end, but I guess I don't believe in probability matching being just probability matching, right? It's like it probably comes from other processes. Yeah. So that seems like an unlikely explanation. But what is potentially happening, what could potentially be happening here is that again, the goal condition is harder. You have a bit of a dual task happening, right? You have to encode this. If you tried it, it's a bit difficult, right? You have to encode this fractal and then remember it later on. So you have a dual task effect happening, which could potentially impact your choice process at the time of choice, right? Making this task harder and so making choice noisier or something like that. Right. So the first argument against this is the reaction time thing. If you had a dual task effect or anything that made the choice more difficult, you would expect reaction times to be slower in the goal condition compared to the familiar condition, which is not there. Something we've replicated a couple of times now. Yeah.
So, this is a question that I don't really kind of. Probably isn't a very answer. A lot of people tried. It's really difficult to provide one. What's the definition for single shot here? That's like a question that plagues people in the machine learning literature, plagues in the AI space, and I'm just curious as you're moving forward, how are we going to operationalize a single shot?
Okay, so Tyler's question is what do I mean by single shot learning? And my answer is that I don't mean single shot learning. I mean single shot goal learning. Okay, so this is a single shot goal. Like it's a goal that you have a single opportunity to use. Okay, I'm not saying that learning is off the stimulus action associations is single shot by any means, but I'm saying that you have only one opportunity to encode this specific fractal as a goal. So it's orthogonal to the single shot learning kind of question.
That's helpful. And then how would you, for example, pull it apart from, you know, just thinking about the work on like options before.
Yeah.
You kind of like represent your actions in different levels of abstraction.
Yeah.
You know, I might also think, well, you guys represent goals in different levels of abstraction. And so this is like the same goal with just different little like substeps.
Yeah, yeah. So absolutely. So you know, I'm calling this a goal. It could be a sub goal. And this is actually a very, you know, I skipped that, but it's a motivating factor for this experiment, which is that the option literature tells us once you reach a sub goal, there should be a reinforcing effect that's not part of the global reinforcement. But do we know how we, you know, like set a sub goal and how the brain would make that reinforcing? No, we don't at all. And so this is like the starting point to showing this. So that's more like a, you know, like, okay, let's establish this and then apply it to hierarchical options. Thank you. Okay, second, we measured in those participants the NBAC performance, and we show that NBAC performance selectively relate to participants' performance in a single shot condition, but not in the familiar condition, which seems to show that working memory selectively correlates with instructive learning. And you can control for difficulty here or sling effects or anything by restricting this comparison to those two bars here where the overall performance is the same, so that, you know, there's no worry of, you know, it not showing up here because you had ceiling or something like that. Okay, so we wanted to try to understand where this came from. So we developed a fairly descriptive computational model of this. So we're not claiming it's a process model. We use, again, the reinforcement learning framework and include some decay and sticky choice, mostly because we can't model other types of contributions of working memory as directly in this experiment. And then we test how parameters depending on condition. And what we find is that the way we capture participants' performance well here is with a winning model that has two learning rates. Again, one per condition, one for the familiar and one for the single shot, and the learning rate is slower. In particular, this model here that you can see very well, the two noise model, is a model that assumes everything is shared, but choice is noisier in the goal condition, definitely does not win. This is exceedance probability. So that's another argument in favor of saying that the reason we see worse performance is not worse choice process or different choice process, but really slowed learning overall. Okay, so it seems like participants are able to learn instrumental values using constructed goals. The choice process appears to be similar to what we observe in classic reinforcement learning tasks, and this appears to show that obtaining the one-shot goal has a reinforcing effect. And it appears also that working memory plays a role in setting this reward function for the goal, with no evidence for dual task interference. Yes.
Is there another kind of interpretation of this kind of goal learning task where it's essentially saying, well, so every now and then I might not have encoded the goal sufficiently well, such that I'm actually not learning for my choice in this trial. Right? So it's just that I'm maybe doing the same thing, but it's just like I'm getting noisier feedback.
Absolutely.
Because I sometimes don't know.
Yeah, absolutely. So so that's what I mean when I say this is more descriptive than process. I actually really think that's what's happening. In this case, so I think what the slower learning rate here is capturing is probably lapses in goal encoding more than actual slower learning rate. It's not something we can it's something we can easily simulate and show you can get the same thing, but it's not something we can easily fit to the data because we can't observe where the lapses are, which makes the fitting process very non-trivial. But I think that's likely what's happening, and we're actually testing a version of the task now that gets a little bit at this question. Okay, so we wanted to go further and ask really whether those single shot goal outcomes were treated as familiar rewards by the brain's neural network, because we wanted to make sure that we weren't actually seeing similar results, but coming from a completely different choice process like this, forward-looking, a category-oriented kind of process. Yes.
I'm kind of curious about if you thought about goal familiarity. I'm looking at those fractals, and I just have a point of it is that you one-shot goal learning.
Yeah.
But to me, I'm kind of curious if you can do one-shot goal learning with more familiar goals. Like I look at those fractals, and it's pretty hard for me to
it's very
make
hard.
sense of them. I'm wondering if you replace those with like common objects, like for one, your goal is a tree, and like the non-chair or something, and you race through those and still do some one-shot goal learning. Do you see the same pattern?
Yeah, so I didn't try it, and the reason I didn't try it is that I wanted as much as possible to control for any previous value people might have for anything. So with very unfamiliar items, you're very unlikely to come in with, I like this one better than that one, although there's certainly some of that it hopefully averages out over people. Whereas if I have, a tree versus a car, there might be, learned value already there. So we were trying as much as possible to avoid that. But yeah, I assume it would be the same.
Yeah. Do you think that it's fair to say that familiarizing the sort of goal part would be injecting that, or I guess sort of taking away from the whole one-shot goal thing? Does that make sense?
I don't think it would take away from it, but I think it would make it much harder for me to convince you of that result, because there could be potential confounds that would be very hard to control for.
Yeah.
Yeah.
Just thought of trying to create a one-shot goal either by making it, either by giving them something really either salient or semantically encodable, or they can compress it really heavily, but still retrieve the value of it. I'm not quite sure tracking what directions you would expect that to
Yeah, so Tyler is asking if I made it less hard on the working memory, if I would still see the same results, essentially, or how it would impact the results. Again, the reason we don't do that, like the simplest way to do that would be to just remind people here that this was their goal or their non-goal, right? But if you did that, then there would be a risk that the word goal itself would be the reinforcer, right? Or something like that. So essentially, any simplification you can do leads to the same kind of risk of confound that we were just discussing in the previous question, which is why we went to such length to do it. So that said, I talk about working memory, but this is really not that hard a working memory task, right? Like, it's just 2 items and then a delayed match to sample, right? Since then, we've tested this task with a modified version where you have to grab the goal when it shows up, essentially. So you have to like press space bar to say like, okay, this was my goal. And people are like have D primes of 4 or 5 on this, right? It's easy. It's actually it's demanding, but it's easy.
For example, took away the forward condition, but instead made it 2.
Yeah.
Yeah. You would expect the results to
yes, although I would expect potentially more working memory contribution to the learning, which might have downstream impacts on people actually using rewards for learning. Okay, so the open question is whether this is indeed treated the same way in the brain, and if so, how the brain converts those goals into rewards. Okay, so you can trace this by looking back at the algorithm here: states, rewards, and actions, learning through reinforcement learning. We assume that this is a representation of what's happening in the stratum, that's learning, the value of choices using dopaminergic reward prediction errors. And the way dopamine computes reward prediction errors by getting upstream inputs that tells it both the expected value, but also the reward you got, right? And so the question is whether this kind of single shot goals that we store in working memory can also fit this information into this reward network in such a way that it can be integrated into a value without us having to get chocolate for everything we're trying to learn in everyday life. Okay. And so the predictions is that the same encoding of single shot goals, we'll see the same encoding of single shot goals and familial value, but in a way that's working memory dependent. And I want to say again that this is not necessarily trivial, that there is an alternative, that there could be a qualitatively different network in the brain that responds to interactive goals, and for example, also in the forward planning manner. I've tried to resist saying model-based, but that's what you could think about model-based reinforcement learning. Okay, so we put participants in the scanner and did an fMRI study there. And I'm going to only show you the highlights of it. This paper is published, so there's more details in there. And I apologize in advance if I don't know the answers because I'm not an fMRI expert. So I create my collaborators here, Sam McDougall, Ian Ballard, and Sonia Bishop for this. So first we found a clear, during this pre-trial period, we found a clear effect of a single shot of a family year. So there was kind of sanity check here, visual areas, because this is such a more complex visual input, but also parietal and lateral prefrontal, which is a working memory network, and hippocampus here, which would be expected for the encoding of those fractals. When we look at the feedback here, we also found this lateral prefrontal cortex activation, which is consistent with working memory retrieval. We did not observe this activation during the choice period, so we did not observe this active maintenance that is sometimes characteristic of working memory. This is super quick. I'm just showing you some highlights, but essentially one-shot goal condition seems to more strongly recruit the working memory network at pre-choice and feedback. But other than that, we don't see any evidence for a specific goal-directed choice process in this task. So what about signatures of reinforcement learning and, for example, effects of valence or prediction errors at feedback or effects of value at choice? So to ask this question, and the prediction here is that the reward network that we can identify within the familiar condition also supports single-shot goal reinforcement learning predictions and representations. Okay, so we use the familiar reward condition as a localizer for those regions of interest. And we find a fairly classic network here with ventral striatum and hippocampus being sensitive to valence, so whether you got a reward or no reward at the outcome. Medial KFC for expected value at a choice, and a few regions here, including striatum, for reward prediction errors. Then we take those regions and test whether the same regressors, this time in the goal condition, also significantly activate those regions. And that's what we find. Strong effects of valence, this time goal versus non-goal in striatum and hippocampus, of expected value in the medial prefrontal cortex, and of reward prediction error in 2 of the 3 regions. It was not significant in the striatum, which had us, wondering why not. To be completely open with you guys, we had a small sample than we wanted in this experiment because we scanned participant N-5 1 day before everything was shut down for COVID. So, we knew we might have power effects here. We did an encoding analysis here in the striatum where we trained an encoder to predict reward prediction errors in the reward condition. And so if it could use this encoder to decode reward prediction errors in the goal condition, and we were able to find that significantly in the goal condition. So this slightly more advanced analysis showed that the striatum also encoded similar information across the 2 conditions. Okay, so it seems like the reward network, as identified by the familiar condition, also encodes valenced reinforcement learning variables in the instructed goal condition. So next we'll ask what the role of working memory is in setting this reward function. And the prediction was that the working memory networks that we've seen activated in the goal condition supports this reward processing activity by priming the reinforcement learning system to interpret instructed goal stimulus as rewarding. So we tested this prediction with functional correlation analysis, where we predicted that, yes.
Sorry, I have a question about the conclusions regarding reward system engagement. So I think I believe the result really does reflect, those things driving it. But you can imagine that the fact that these are mixed in with trials where you're getting this kind of monetary reward might lead you to frame any sort of, congruent feedback as being like a monetary reward, right? Whereas if you were doing this, only doing the single shot goal trials, right, and maybe had it framed a little bit differently, you might imagine people wouldn't necessarily interpret them in the same way. I wonder if you have any thoughts or if there's anything that would lead you to sort of discount that.
Yeah, no, that's hard to discount. And I think it goes back to the goal versus sub-goal kind of question. You can also, a similar kind of question you could ask is, we didn't actually convert points into money in this case. And so in a sense, the +1 and 0 is also fairly abstract. Although that's the typically used, kind of reinforcer there. And so there is always in these experiments like an overarching goal, which is to please the experimenter, right? And that's shared across both. And so in that sense, you can always ask, well, how different is this really? So I think, the way we think about it is that those overarching goals are shared across the 2 conditions, but there's one thing that's separate in the sub-goal, single shot goal condition, that does impact behavior to a degree, and is related to working memory function in a way that the other one is not, and so has to have a slightly separate input process to it, making it non-trivial whether it would really work the same way or not. But I agree, there's a little bit of a chicken and egg issue in this question, which makes it sometimes a bit hard to think about. But yeah. Okay, so we're going to use functional correlation analysis to see whether stronger encoding in working memory of the fractal prefers to the choice leads to stronger or more reliable feedback signal at the outcome. So we take this pre-choice prefrontal cortex activity and we mask it with a working memory mask here that's taken during the end-back task to get this region of interest in the lateral prefrontal cortex. And we do pre-choice 2 feedback connectivity to ask whether stronger encoding here predicts stronger encoding at feedback. And we do this in the regions in which this feedback is represented, so in the striatum and the hippocampus. And long story short, we find stronger connectivity index between prefrontal cortex and striatum and prefrontal cortex and hippocampus in a way that reflects the individual differences between the conditions and individual differences in working memory condition. And that is specific to those regions. So we have a control region where we do not observe this. We also did an exploratory analysis where we tested more directly, well, does this go actually through dopaminergic signaling? So we took an anatomic region of interest of the DTA and tested this connectivity. And we also saw stronger PFC to VTA connectivity in the goal condition compared to the reward condition, although this one was not predictive of individual differences in behavior. Okay, so some takeaways that we take from this is that learning from one-shot sub-goal stimuli, they rely on the control network in working memory, and that it drives a canonical reinforcement learning neural signatures rather than a separate goal-directed network in the brain. And so that essentially we might be recruiting those old networks in the brain via top-down cortical inputs that prep those circuits to transform those novel goals, like finishing your Sudoku grid or turning your phone red into standard rewards like chocolate or thing like that. Okay, so I hope I've convinced you of the important role of executive functions and in particular working memory, not just in being a learning or decision-making process that's important on its own, but also in setting the stage for how other circuits like reinforcement learning operate and enable flexible type of learning in humans. And I'd like to thank you for your attention and thank my lab members, in particular Sam McDougall, who's now has his own lab at Yale, but was a postdoc in my lab. Sonia Bishop and Ian Bard. I think you guys know Ian, he was grad student here. He's a postdoc at Berkeley now. Who contributed a lot to the fMRI experiment, and also Milena, who's my grad student here, who did the choice project. Thank you.
Does anyone on Zoom have a question?
I have sort of a high level question, Anne. So something I've always kind of wondered and asked a few of my colleagues occasionally is how we come to value situations that are really outside our experience, like say getting tenure when you've never done that. And it feels like to some extent, that's what you were addressing by talking about the value of sub-goals, but it also feels like it's unclear then why I would come to decide that a sub-goal is so urgent. Do you have any thoughts on that?
Yeah, so two thoughts. One is that I think the example you give, that might be, a case of generalization. So we know there's, like social components to rewards, right? That are very important, actually close to primary types of rewards. And in the case of tenure, might be something, that you could easily generalize, as being a novel, completely novel state, but is similar to other high prestige kind of situations that you can set as a valuable state. The second aspect of your question is how you decide a sub goal is valuable. I think is a $1 million question in AI right now, and is also $1 million question, I think, in cognition. I don't think we have, there's a ton of theories out there, right? Like of people trying to figure out how we set sub goals, and looking at various aspects of statistical regularity or, betweenness or, various reasons why you might set something as a sub goal. And the question, the causal question is interesting, right? Do you decide that something is a sub goal because it's valuable, or do you decide that something is a sub goal and then assign value to it, right? And I don't think we know that either, right? So, I don't have a better answer than that, but I think I think I'm trying to frame this question saying, well, here we've definitely ruled out, well, we've tried very hard to rule out the, already has value aspect of the goal, and we've shown that you can attribute value to it in a way that's reinforcing. So it definitely enables this second interpretation, potentially, that you're choosing a goal, and then that imbues it with value, right? It certainly doesn't rule out the other direction, which is very likely, right? That you choose something because it has value and you've given this value for some other reason. I think both are true.
Thanks. Yeah, that's interesting.
So Rosa asked a question. Rosa, do you want to unmute and ask it, or I could?
Yeah, sure. I can ask. Yeah, so I was just wondering if you could say more about how top-down cortical input might do this prepping of RL circuits to interpret novel stimuli as rewarding.
I really don't know, and I wish I did. There's certainly pathways through which prefrontal cortex communicates with subcortical regions that you could imagine, not necessarily like single path, but multipath. Could do that, but really to test that, you'd have to go, measure really specifically there. And I think here I'm going to be a little bit in a bind, because I think this is a fairly, I really like to collaborate with non-human researchers who can go measure stuff like that. But I really think this super dynamic allocation of reward is fairly uniquely human. And so it's going to be pretty tricky to figure out a way to test that in such a way that you could go, measure in a rat's VTAR and prefrontal cortex at the same time, or something like that. So I don't know. It's the short answer. Sorry.
I guess I was just wondering if there are any other examples of some circuit just being rapidly repurposed for novel inputs.
So one reason I went into this whole project thinking on how to change to succeed is that people who measure dopaminergic activity, for example, see all kind of signals that are not purely a reward in there. One of them being, for example, novelty, where novelty signal drives dopaminergic activity in a way that's that can be seen as similar as a reward prediction error. Something that I think of as even more interesting is information. So I think there's Ethan Bernberg-Martin who's done really cool experiments in monkeys showing that animals are willing to give away rewards in favor of obtaining information, and that this information shows up in the dopaminergic activity, right? And in that sense, to me, this is something you could interpret as being, a specialized input to dopamine, but you could also interpret it as being one type of goal that the animal might have to get more information, essentially, and that this value, because it's a goal, is going to be imbued with value. that will be driven there. So I think there are examples out there, but I think they've been largely interpreted as, multiple separate aspects. And it's going to be, very non-trivial, I think, to show whether, there's a shared mechanism behind that. Mostly because I think it's a hard to do, the type of question that's hard to translate to non-human animals.
Thank you.
Okay, so we're at time. Let's give them another round of applause. We have snacks and drink outside, so we're welcome to take a conversation here. Otherwise, thanks for joining, everyone.
Thank you.